Alright, here's part 5 of my LinuxCNC HAL tutorial. In this one, we're going to cover how to use an Xbox 360 controller with LinuxCNC. So you can jog around, trigger external relays, like with the crosshairs we've been working with, and also call subroutines, like this one that removes the offset between the laser and the plasma head, and then re-zeros your axes. To be clear, this is an Xbox 360 controller with a cable and a USB plug on the far end, and this will work right out of the box. You might also have luck with a wireless 360 controller, but I haven't tried one, so I can't say for sure. As far as I'm concerned, I went the cable because copper is simple, and copper you can trust. Whereas wireless, not so much, right? Either you might have weird driver and software issues, or the plasma torch might put out too much EMI, make the connection drop, and there's things I didn't want the risk having to debug. So I went the cable, and that works great. So long as you don't drop a piece of plate in it and sever it in two. But we'll get to that in a minute. So the Xbox 360 controller does work. I will say I did try an Xbox One controller briefly, and that did not work. As far as I could tell, Linux didn't have the drivers to even see that you plug the controller in. So you might be able to fix that by getting the controllers after the fact and installing them extra. But when that one didn't work out of the box and this one did, the answer should be pretty simple, right? And also to be sure you get a regular, official Microsoft controller like this one here, and not a Tunisian knockoff, because this one does not work. This was, I think, 12 bucks off Fleabay new. This one was $25 used, but it's worth the extra money because this guy doesn't cut it. The problem with it is the connection drops out randomly. Even though it is cabled, this copper, Chinese copper, you can't trust. Ugh. So 10 minutes if you plug it in, or 20 minutes, or an hour, 2 hours, 4 hours later, absolutely no correlation to when it would drop out and anything going on in the shop. Just entirely randomly, it would lose connection. Now you can make it visible again by either unplugging it and replugging it back in, or refreshing the connected devices, and then Linux will pick it up again. The problem with it is that the HAL component we used in LinuxCNC to work with this does not see it come back in unless you restart all the CNC components in Linux as well. So you got to close Access out and reopen it again. And you just can't do that willy-nilly, right? If you're in the middle of a 3-hour G-code program, you can't close it out and reopen it just so the controller works again. So this guy, it's not worth the savings. It's not saving anything at all, okay? It's just making a pain in the ass for you, so don't bother. Now, I bought one of those because I originally had an Xbox controller that I had broken by dropping some plate in the cable and severing it in two. But I did later go back and fix that, and it turns out it's really not that hard to do. I just got a 12-foot phone charging cable with nylon braiding on the outside. Hopefully it's a little bit more skookum, and some foil wrap shielding around the interior cables. And you pop the casement open, and you find where the old cable had been crimped and then soldered in place. Simply desolder it, lop one end off of your phone charging cable, split the wires out, and then solder them directly in the holes, matching color for color. Add some hot snot as a strain relief, and you're good to go. I tried this one for I think about 2 or 3 days, just practicing with it and making sure that it would not drop out randomly, and it didn't seem to. So I think this is, good enough. Now I've continued using the unrepaired one here, simply because I've already gone back and kind of padded out the cable with some nylon webbing and paracord, just to kind of beef it up a bit. But if you do have one of these and you lop the cable in two by mistake, I would not hesitate to try repairing it this way, because it's an easy fix and waste not, want not. Now there are 2 ways you can set your controller up. One is as a dumb keyboard emulator, and the other is directly in HAL with the HAL input component. They both have the pros and cons, namely that the keyboard emulator is simpler but has fewer features, and then the HAL style is more complicated but does more stuff. So we're going to combine the two to get the best of both worlds. Now the keyboard emulation is provided by QJoypad, this program here, which you do need to install separately. If you're familiar with Linux distributions based off of Debian, like this one is, you'd think you go to the command line and do sudo apt-get install QJoypad, and then be on your way, right? Wrong. Of course, it has to be more of a pain in the ass than that, right? The problem is that LinuxCNC 2.7 is based off Debian 7, a very old version of Debian. So for one thing, the software sources that apt-get looks to have already been moved off of the archives. And then even if you fix that problem and tell apt-get to look to the archives for it. There wasn't a package for QJoypad until Debian 8, the next version. So what you end up having to do instead is basically go online and find the package for QJoypad, that deb file, and install it manually with sudo dpackage install QJoypad like that. And then you're good to go. Now the details and everything and the reasons for that are kind of beyond the scope of the video, but I will include some links below and some further instructions either in the video description or over in the GitHub project. And if you just follow along with the instructions there, then it'll be fine. It's not that bad. It's just aches and pains to deal with when you're working with an older version of Linux. But once you've installed it, then you can go over to the menu and under Games and launch it, and you get the little icon over here. Right-clicking this lets you update the joystick devices, which you need to do once you plug the controller in, so LinuxCNC will see it. And then left-clicking brings up the menu where you do all of your button selections. So the first thing you want to do is hit Add to give a name to your layout. You start off with no layout. I name mine Test Layout just to give it, a name. And then when you're done setting all your buttons, you can hit Update to save. And that way you'll have the same configuration when you start your computer next time over. Now for each axis and button on the controller, basically pop the menu open, and you look at it right now, when I hit the joystick, boom, right, you can see what exactly you're hitting. So if you're not sure what axis 1 is, that's on the joystick, and you just kind of bumble around till you find the button that you're hitting matching the button you have the menu open for. So I have this one set, so this basically corresponds to the up and down keys on the keyboard, and then when you're in axis, those are the buttons you use to jog. So that's how this ends up being a really easy way to set up jogging from the controller. Now you also got these little sliders here, which you can use to set a dead zone on the joystick, which is nice because the joystick doesn't always come back to 0 when you let go. So you can see right now it's actually a little bit to one side. So you want to set these sliders too, just so your machine doesn't creep when you're not using it. So basically go through one by one, set all those up, update, and then close the dialog. Don't hit quit or you're going to quit out of QJoypad. But yeah, basically it's pretty simple, pretty straightforward. The one big caveat I want to provide with this is that since you are just using it as a keyboard emulator, it basically it just types keys. So right now I'm hitting one of the buttons on the controller and I'm typing out a bunch of I's. So if you either have your mouse focus in a different program, right, or it's just not on the right tab on the Axis GUI, your controller isn't going to work. So one button you probably will want to set up is having F3 on a key. That way you can always come back to manual control, and that way your jog is easily working. And everything else you want to set up here, you'll find, let's see, in the quick reference, the full list of shortcuts that you can pick from, all the different keys. Now, as I've mentioned before, the shortcuts in Axis kind of suck, but in video, I think number 2 on the INI file, I did give a brief overview of the Axis RC file that you can use to tweak some of these shortcuts if they're not to your liking, as they were not for me. Now it's on to the good stuff using HAL. So going over to the Git project for this and taking a look at the diff view, we can see between part 4 and part 5, I did 3 steps, 1, 2, 3. And in the first one, I began by adding a new file, 20-xbox.hal. And we made some edits to 40-laser and 99-post GUI, which we'd also worked with in the prior video. Now, since I added that new HAL file, I had to come back to the INI, as always, and then slip that here in the list of HAL files for LinuxCNC to load. So now let's look at that 20-xbox file as well. So if I do a git checkout, like that, and now let's see, configure to do, and then here we are. So the first thing that should jump out at you here is the use of loadusr instead of loadrt. What exactly is that? Well, loadrt is for loading real-time components in the kernel, and loadusr is for loading user space components. Not that that explanation really explains that much. I guess to put it in simple terms, the kernel is a program that runs all of your other programs. It decides what runs when. So most of your CNC shit runs in the kernel in real time, right? So it can be precisely timed because it decides the timing. And that's how your step pulse generator keeps up with what the motors and the drivers need. User space programs, on the other hand, as regular programs, only run when the kernel lets them. So it's usually enough to make things seem like the real time and that they're running continuously, but in reality, they're not. So loadusr components are ones like this. Not the fastest, but they're still plenty fast for most purposes. And they actually run in separate processes. That's why you don't have an addf to add this component to a kernel thread, either the base thread or the servo thread, because it's running in its own process entirely separately. In fact, if we, let's see, do a ps-ef grep for HAL, probably see, yeah, down here there's a line for the HAL input program actually running separately right now. And from the looks of it, it's just a Python script. If we do a file, user bin HAL input, sure enough, it's a Python script, and we can view that. So yeah, it's just a plain old Python script, and only, let's see, about 200 lines long. It's not even all that big. And a lot of it seems pretty straightforward, making new pins for dash counts, is pos, is neg, scale. Yeah, really not all that bad. So if you know how to write some Python, here's a pretty good example for you if you want to roll your own component later on. Say if you have like an Arduino-based THC, right? And it's putting out voltage readings over the USB, and you want to read those, make them available in HAL directly, you can use stuff like this as a working example on which to base your own components. And I think there's also more documentation on this in the big old PDF. Let's see, this one right here in section 14.14. Anyway, back to our HAL now. So we got this W option here on loadusr, which tells it to wait until this component has finished loading. Then the name of the component, HAL input, and the -kral, if you look at the man page for HAL input, tells us that it's basically loading. Let's see, where is it? Here we go. Load the keys, the absolute values, relative values, and LEDs. So basically, load all the things. And then we pass in the name Microsoft, which comes to the fact this is a Microsoft Xbox 360 controller. And reading here in the man page, it says to look at this special file. Things in the, let's see, the proc directory of your Linux system tell you what different processes running, and then on the bus, in the input and the devices, we're going to look for what corresponds to our Xbox 360 controller. So scrolling down, you see like the power button for the computer, you see HDMI port, audio things, and eventually we get down to the Xbox 360 gamepad. So basically take the string from here, Microsoft, and that's enough for the HAL component to match on that, and then you can use it in your HAL. With that much done, we can have the Axis GUI running, and then pop open a halmeter, and then scroll through this to see what pins we got from including HAL input. And eventually we get down to here. And we got all these different input pins, all corresponding to things on the Xbox controller. And we got stuff like button A, button B, button Y, button X, pretty straightforward there. Not all of them are so clear, which one is TL and which one is TR. For that, you pull up the controller again and hit the buttons while you're looking at this here to see what that goes to. But yeah, what we're going to do now is just take a few of those buttons, the straightforward X, Y, B, A, and then hook them up to signals that we can use later on in the rest of the HAL files. Remembering from the last video that the order of these HAL commands isn't super important, as long as things get defined before they get used, and that modules don't get loaded multiple times. So here we're just going to take the output pins that we get on the controller and hook them up to signals and do just that 1/2 connection for now. And later we'll hook these signals up to input pins. Now yes, these are all output pins giving the status of the buttons, even though they are in a thing called input. That's because this is all from HAL input. Some of these names, a little bit silly, but you think about it, it does make some sense still. So now taking a look at the 40-laser HAL file, we see the diff mode is an absolute mess because I made a whole bunch of really small changes. So instead, we'll take a look at the file directly. Now the changes here are mostly around taking out that OR2 component we had and swapping it in with a logic component instead. So take a look at the man page for logic. We see this is a more general Boolean logic component. So you can give it this thing called the personality. And it's a very silly name for a variable again, but what this does is it defines the output styles that your logic component gives you, as well as how many inputs it takes. So you can see the personality parameter is a combination of, hexadecimal values. So if you have a 1 in that first position, then you have an AND output. If you have a 2, you have an OR. If you have 3, you have both ANDs and ORs. And then 4 can give you an XOR, which is another Boolean, another Boolean logic thing entirely. But basically, you can combine these to give you the output styles that you want, and then the other 2 digits are for how many pins you want. Again, this is an hexadecimal, so it's counting 0 to 9, and then it goes A, B, C, D, E, F. Read Wikipedia on hexadecimal if you don't know that already. But yeah, so it gives you a function. You need to add f, which will be our logic.0. And then since we're doing ours with the OR personality, we have a logic.or output, and we have input pins for 00, 01, and 02. So going back to the file here, we see all like that, that OR dot in1 is now in-00. Just a small change. And we did those changes throughout, and then also added this special line, right, for doing a net connection between the signal for Xbox, the B button, to that logic component. So now we're taking all 3 inputs, whether it's G-code, the PyVCP checkbox, or the Xbox B button, and then putting them towards the parallel port pin 16 out. And then over on the PostGUI file, we did just that one change on the OR2 now to the logic component as well. In our next commit, we make some more changes to 20-xbox.hal just to give ourselves signals for a few more of the buttons. Now the names on the buttons themselves and the names given in HAL don't line up precisely. Like button-tr is the top right trigger button, and then let's see, RZ is the lower trigger button. So I named them, the signals here, in accordance to what the buttons are physically labeled on the controller. But you pick your signal names as you want them. And then the bottom trigger button on that right-hand side is actually a potentiometer slide. So it can give you a whole array of values, or it can give you just a Boolean for whether it's positive or negative, based on which pin you want to pick in your HAL. So for our cases, we're just going to use it as a Boolean value using this pin right here. Again, just kind of bumble through the halmeter and hit the buttons and see which one reads out what values for what you want to use in your HAL. And then I'm adding a few more here for the D-pad. That's the plus shaped one on the left-hand side for the left and right keystrokes on that. And again, just using the absolute value, but whether or not they're positive or negative. Now, if you remember before in our ini file, we had a few of these MDI command options, which I said we're going to use later on. Well, now is later. So what these guys are shortcuts for different MDI commands you can issue and then trigger via HAL. So you can have up to 64 of them, just listed one after the other right here. And then these, let's see, correspond to pins, let's see, like this, halui.mdi command dash, number right there. So in here, I defined one of them that will zero out X and Y, another one that zero out your Z. And then going to the 99 PostGUI file, we can see I hooked these up to one of the right trigger buttons, another one on the left direction for the D-pad. So some very straightforward net commands give us the ability to now zero out the machine from the controller. And nothing says that these signals here have to be coming from HAL input either, right? You could use like real buttons hooked up to your parallel port pickup board or things on PyVCP, right? HAL doesn't care where the signal comes from. It just needs a signal to feed this input right here, and then that will trigger the MDI shortcut for you. Now, you probably noticed the MDI commands listed in that ini file then correspond to pins 00, 01, 02, all the way down to 63 for the 64 commands you can have. Now, that means if you take out a command, like you pull the command out at the top of your MDI list in your ini file, then all the ones beneath it end up shifting by one number. So do be careful about that. If you want to remove a command from the ini file, I'd recommend turning it into a no-op instead of really deleting the whole line, because otherwise you'll mess up all the other numbers in your HAL. Also, since these net commands are hooking up to the HAL UI component, they have to be listed in the PostGUI HAL file. And in our last commit, we're going to make our first subroutine and then also hook that up to the Xbox controller using the MDI commands and a little bit of HAL. So in our ini file, we add one new MDI command that does a call on the subroutine. And then in the PostGUI HAL, we hook up the RT button to MDI command -02. And that's the one that removes the offset between the plasma torch head and the laser. Now the G-code file itself, since that's all brand new, let's look at that in a regular old text editor. And I will say, quit this, check out HAL part 5, and then we can go back to the subroutines directory. Now this directory is important because in the configs, we specified that here in the ini file. And that way, when we do a G-code call, it looks in this directory for our subroutines. Now, there are some requirements about the format of a subroutine. For one, the function inside has to have the same name as the file. So laseroff.ngc has a subroutine inside called laseroff. So I will preface this by saying, I personally don't know shit about G-code. It's a very crufty, archaic language. I'm kind of learning it as I go along, and there are probably some things I'm doing here that are not the right way. So treat this more as an example of what you can do with this, as opposed to what you necessarily should do with this, right? So we have an O tag here at the top, marking it as laser off and starting the subroutine. At the end, another O tag ends the subroutine. And then we are putting these values here as offsets into a couple variables that we will use down below. Now these were measured off the plasma table to get that offset between the laser crosshairs and the plasma torch head. The method I used for that was pretty simple. You set a plate up on the table, you put the torch somewhere over top of it, do a G92 X0 Y0 to make that spot your 0, 0 coordinates, and then do two cuts, 1, 2, in kind of a plus shape, right over the 0, 0 mark. And then you can take your laser, line that up over that plus you just cut, and then read the DRO. And then that's where I get these numbers from. And of course I put them in here with 4 decimal digits of precision because my plasma table, it's that precise. Anyway, so you save these in these variables, and then down below, we save the position that we are currently at. So LinuxCNC has some built-in variables, underscore X, underscore Y, underscore Z, that give you the current location of where you are right now. And these are aliases for parameters otherwise called 5420, 5421, etc. Right? You can see just how crufty G-code is, right? Like 5420 is the name of a variable that says where you are in the X coordinates. Anyway, if you look at the documentation and you search for this number or search for underscore X, it'll show you, and give you a whole list of the different built-in variables and what they're for. So you can start learning all this, old cobweb-filled malarkey yourself. So we save our coordinates in these two variables here, and then use G92 to shift our entire coordinate system. So without moving the machine around at all, we tell LinuxCNC to read out our position off by the offsets. And then we use G0 to move back to the position we just saved, and that in effect puts the plasma torch head where the laser diode was pointing just a moment ago. Now that's probably not the right way to do it. Like I know you have like G54 and like a billion different coordinate systems included in G-code. I just haven't gotten as far as to learn all of that yet. You're writing G-code by hand. It's a thing to learn. So I'll get there, but for now this does seem to work, and it's a decent enough way for me to line up my work on the plasma table and cut a job where I want to cut it. Anyway, that's all for this video. So to give you plenty of ideas as to what you can put on your own machine. And just take the inspiration and run wild with it, right? It's your machine, so make it do what you want. Now, as always, you're welcome to like, subscribe, and most importantly, share this video to help spread the Linux love. There'll be some other links and important information down in the description below, so make sure you don't skip that. And if you need any help, just drop a comment. Now get ready for part 6, in which I'm going to tell you how I do unlock probing with my plasma torch to fix the Z offsets before every cut. But until then, peace.